right, thanks for being here today. I'm so glad you guys made it. There's so many activities going on the same hour, so thank you for coming here. Again, my name is Marek Litomisky. I'm one of the academic counselors here, and I am the lecture coordinator for science. So thanks for being here. I appreciate that you guys are here. I'm not going to talk too much because the stars are here. I'm just going to give you a quick surprise to the group. There is a $200 honorarium check provided by William Golke for the honor of his parents. That's going to go to Tom, the grant coordinator, and he's going to use that money for the academy. So I'm going to hand that over to Tom. But I wanted to just present each speaker with the Mike Gatto Certificate of Recognition for coming today and speaking to us about their Robotics Academy. So I just wanted to present those, and then I don't really want to spend time with the biographies. You could read that online. I just want to really focus on their presentation. But first of all, we have the mentor and faculty, Richard Ohanian. I'd like to present you one first. And thank you for your guidance, and thank you for helping these students with their academy. Thank you so much. And no particular order, Ernest Hovhannisyan. And Roman Zograbian. And Marek Litomisky. And last but not least, Hoon Kim. So with no further ado, there you go, Robotics Academy.
Thank you, Nora. Thank you for the introduction, and thank you for the certificates. I'm sure that $200 is going to go a long way. Hello, everybody. Thank you for being here. I wanted to introduce myself. My name is Richard Ohanian. I am an electrical engineer working full-time job at Jet Propulsion Laboratory as a RF and microwave engineer. And at nights, I'm also an adjunct faculty here teaching electronics and working with these fantastic four that we are going to hear their story today. So let me start with a story. Almost 2.5 years ago, I was sitting in my office at JPL. My supervisors came to me and he said that, hey, there's this new project, why don't you want to join the meeting? I went to the meeting. In the meeting, I saw a young guy. Later, we got to know each other, Professor Thomas Voden. He was spending the summer at JPL at the time. So we started a conversation on how engineering is, how it should be taught. You know, I told him my opinion about how things should be, and he started basically sharing his stories of, hey, you know what, we have a Robotics Academy at the GCC. So basically, everything started from there. Of course, there is a long history of robotics clubs at Glendale College, but I wonder if Tom and I didn't have that conversation, I don't know what would have been the outcome today. But so basically, the gist of the conversation was that we thought, that was our opinion, of course, there is a structural issue with how engineering is taught at colleges. So basically, the way the students are being taught engineering, most of the time they go through a long sequence of math and physics courses for 2 years, and it sort of separates the students from the very hands-on experience, practical stuff that students want to basically get their hands on with and learn from. Traditional engineering courses also have a lot of prerequisites, so again, it sort of delays the process of this for the students to actually do hands-on projects. This might be the reason that there is sort of a low success rate with physics and math, because these courses, I mean, we should at least sort of give credit to, they are necessary, but at the same time, they're abstract. So when we teach students 2-3 years of math, they don't exactly see where this is applicable. And also, when they want to transfer to university, I had a lot of students coming to me and asking to me that, hey, you know, I want to transfer to mechanical engineering, electrical engineering, but I really don't have any idea what it is, because I never had a chance of taking a real engineering course to sort of understand that, hey, this is going to be my major for next 2 years, and God knows it's probably going to be my career for 30 years, but I want to understand what this is. So taking, again, like those introductory physics, math courses were not enough. So therefore, why robotics? Robotics is interdisciplinary. It is hands-on and fun. It is relevant and achievable. It is relevant in the sense that, hey, it connects the theory to the practice. It's multidisciplinary inherently. Why? Because it involves electrical, mechanical, software coursework, and also system engineering. And it's really fun. So these were the courses that in the process of probably 2.5 years we at Glendale College introduced, and we're still introducing new courses. I'm going to actually go through them and introduce them. The electrical focus, these are the courses that are in the process or we're teaching. Electronics and electrical circuits, introduction to digital electronics, and electrical engineering fundamentals. So students taking these classes, especially the very first two, they don't need any prerequisites. The last one is a formal articulated course to CSUN, but the first two, the students don't need any prerequisites. Mechanical focus. Introduction to robotics, very fun class. VEX robotics students learn how to do mechanical, electrical, and software, but at the very, very introductory level. Engineering 152, that's traditional statics course. And engineering materials and science, we're still working on this, but hopefully we're going to offer it soon. Then there's software courses. Object-oriented programming in C++, robot motion planning, which we need to rewrite this course. It's going to be in C++. Right now it's in Python. And also MATLAB. Sawada is teaching those courses. Sawada Isayan sitting among the audience. So, and the last course, which the way we design all of this is that students are taking these courses, and basically everybody comes to the Pinnacle, which is 1 year, 2 semester engineering 298, 299 coursework, back-to-back 2 semesters of undergraduate research. It is a transformative active learning experience, and I will explain what that means actually. So the students learn the very subject that they want to learn by going through a productive struggle. We, the mentors, there are 3 mentors, electrical, mechanical, and software. We don't actually teach them stuff. We help them figure the things out themselves. So they have to go through the process. They have to actually design the circuit, design the mechanical, design the software portion, and of course, most of the time fail. Good thing about this process is that they learn through failure, and it works. So as I said, there are 3 teams, software, mechanical, and electrical. Each team usually has 4 or 5 students, and there's a mentor, which is, again, 3 mentors, electrical, software, and mechanical. And these mentors have industry experience. So they are full-time employees at, well, all 3 of them are at JPL, but they actually implement whatever processes we have at JPL during the design process of this class. Technical hands-on experience. So most of the students learn, again, as I said, most of the students learn through doing stuff. This is action and active learning. They also learn project planning, execution, and management. They learn communication, leadership, teamwork, and collaboration. Science is, my opinion, science is best taught and learned in a collaborative environment. Also, when you do teamwork, things work out much better. And that's how the real life, real world companies or organizations that do in the industry, they actually want people that know how to do collaboration, know how to do teamwork, know how to do project planning. And our students do that themselves. And we just guide them through it. Of course, most of the time, or sometimes they fail, but that's okay. It is a startup environment. I mean, literally, we have difficulty kicking them out of the lab. When we go to the lab, there are coffee mugs there, they're drinking coffee, working hard, probably through midnight. So that's why this process maybe can be responsible for next Steve Jobs or, Mark Zuckerberg, who knows. This is actually sort of a garage startup environment that I think it's helping the process in terms of them learning and having fun with it. It is rigorous and relevant. This is not a club. I mean, the things that they built, they're going to talk about. These are serious projects. This 3D printer, the electronics, the mechanical, the software, and also that 4 degree of freedom arm, these are at the senior or even master's level projects. but they build it here themselves. And it's a resume builder. I interview people at JPL. If I see something like this on somebody's resume, I will get them. I will have no hesitation in hiring any of these 4 gentlemen because I know them. I know they can deliver, and that's really, really important. So what have we accomplished? We jump-started a formal, collaborative, and transformative Robotics Academy program at Glendale College. We created an inclusive and fun and active learning culture and environment. The culture is important. Our lab, SB161, became sort of this hub place that everybody wants to go. They want to hang out. They want to see what everybody else is doing. They talk to each other. They become friends. Important. These are very, very important soft skills. And we also introduced new relevant courses at GCC, and we are implementing hands-on projects. These are the projects, and more to come. How do students benefit? Well, they get internships. By putting these experiences on their resume, obviously they can get internships because people are looking for these kind of skill set, technical and soft skills. They build a relevant real-world theoretical and experimental hands-on experience. They learn practical wisdom by implementing these projects. They learn teamwork. We are basically producing skilled workforce. And also, something about this honor system. So we noticed that somehow this culture of trust and collaboration and respecting each other was developed when our students were doing this. And this is, again, very important because the network that they built here can go a long way. They can attest to it, but they became, at the very beginning, they were not even talking to each other. Now they're best friends, and this is really valuable. So how do we measure our progress? Well, by number of jobs and internships that our students get. Ernest got an internship, Kevin got an internship too. I'm sure these 2 are going to get internships and jobs pretty soon as well, and the rest of our students. Students transferring to 4-year schools with a better understanding of what they're transferring to. I mean, they understand better the very subject that they want to transfer because they get a feel for it. And students simply will not leave the lab. We think this is a very good measure of how successful the program is. And also, we do surveys and questionnaires, and in all of them, they actually rank the program very highly. This is sort of our methodology that I kind of want to always talk about, Benzo's sword. So it's a Zen story. There was this guy in Japan that wanted to learn swordship. So his father disowned him because he was not good at swordship. So he goes to this very famous master, and he tells him, hey, listen, I want to learn to become the best swordsman. The guy says, nope, can't do it. He says, what if I work very hard? Nope, 10 years. What if I work day and night, very, very hard? 30 years. The guy says, hey, I want to learn this thing. You're just keeping at the numbers. What's going on? So the master says, Benzo is the master. The master says, you're too much in a hurry. If you want to learn something, you have to be patient and just listen to me. So that's the process that we're actually doing it in our labs. We don't just throw stuff at people. The way we actually guide them through our mentorship, I call it passive active mentorship. We are patient and they are patient at the same time, and it works perfectly. So these are the projects. And without further ado, I will invite this fantastic 4. That was it for me. Now Roman Zograbian is going to talk about the projects.
Thank you, Richard. Okay, so we didn't know where to put this slide, but we figured let's put it in the beginning because it makes a lot of sense. So, and you'll understand why. So this is what it says. Theory is when you know everything and nothing works. Practice is when everything works and no one knows why. However, in our lab, theory and practice is combined. Nothing works, no one knows why. It's our own version of Murphy's Law, but basically this is like what we've been dealing with the whole year. Last night, this printer was working. We came in, temperature changed like 2 degrees, stopped working. I don't know, we plugged in the USB, stops working. So yeah, stuff like that. We've been dealing with it and you'll understand why. So if you guys have questions as to like, why did this work? We don't know. Why did this not work? We don't know. It is what it is. So that's fun. And I'm just gonna kind of go over the outline of what we're gonna be talking about. So first is gonna be our goals, approach, organization, processes, the values that we learned, and the values for students who are also interested in a project like this. And then the best part, the projects, which we'll talk about. So I'm going to pass it over to Ernest, and he'll give you a short introduction.
Thank you, Roman. There we go. Hello, everybody. So I'm going to talk to you guys about the goals that we try to go with in our project. It's happening again. Okay.
That's why we.
Nobody knows why.
That's why we did it.
Okay, so we have these goals that we try to go by to find a suitable project to pursue in the academy, because these projects are kind of tough. So we have to make sure that they're doable. So the first thing that we do at the very beginning of the semester is we pick a specific project. So for example, we have a 3D printer and a robotic arm. If you closed your eyes and you had never seen these before, and I said 3D printer and robotic arm, you would probably imagine something different. And this is basically what specific is about. If we don't sit down at the beginning of the semester and define exactly what we mean by 3D printer or a robotic arm, we'll spend probably the entire year chasing something that we don't know. So it's like chasing a ghost. You don't know what you're going to build. So it's important for us to have well-defined parameters. So for example, this 3D printer, we said is supposed to be 13 by 14 by 8 inches. That's the print bed size. That's how it is. This process of abstraction, of imagining what a robotic arm is, and then slowly adding details to it to come to a core project that we're trying to pursue, is how the team stays focused. So from the very beginning, everybody knows what they're going to try and make. There's no confusion about that. The next thing is, did I do it? Okay. The next thing is measurable. So if, for example, Richard threw us a project and we were to work on it, and basically we were waiting for the result at the end of the year, well, we would be in pretty bad shape, because most of the things would not be working. So what has to happen is that it has to be measurable. So our milestones have to be reached at a certain point in time, like every week or every couple weeks. So if we were to just kind of run after the project and not take a modular approach to it, then the subsystems would never work. So the different parts of the printer would never come together and everything would fall apart. So instead, I mean, in a normal class we have tests, right? Every now and then you have a midterm or a test, you take a test, and we know if you learned or not. If you fail it, obviously you haven't learned. It's a similar thing in capstone, only we don't really take tests. We deliver a presentation, or sometimes we test a circuit, we make sure things are still working, and that's how we basically keep track of how the project is progressing, if it's too difficult, if it's too easy, things like that. And then at the end of the year, you don't have a mess of stuff that doesn't work together. Until last night, of course. So the next thing is achievable. 3D printers and robotic arms are not easy projects, I can tell you personally. And they're not cheap. That's another thing I can tell you. We're very, very blessed at GCC to have the equipment that we do have, because it's tens of thousands of dollars, more than that actually. So one of the things is that the project must be affordable to be funded by the program. If it's too expensive, then there's no point in pursuing it, because we're not going to be able to buy the correct equipment or components. The next thing is that it's easy to go overboard. So when we started when we were doing the specifics for the printer, we had so many things that we added on that, it was getting out of hand. So we had to slow down and cut more than half of it off and just say, okay, let's just build a printer. And the other thing that goes in with that is the prerequisites. So as Richard said, we're trying to keep the prerequisites low so that students from many different backgrounds can come in and join in on the project and start working on it. If the project is too difficult, then they can't really do that. They don't have that freedom. But if we make it sufficiently easy, then basically anybody can come in and join in. Easy is relative. This stuff is not easy. The other thing is relevant, like Richard said, this stuff would be kind of pointless if it had no point to our personal goals, our degrees, or whatever we're pursuing. So it gave us a new perspective of engineering, because most of the engineering classes that I think I've gone through, almost all the engineering classes here, they're very different from what we did in this course over here. And this one was really an eye-opener. It definitely was. And the other thing is the technological rigor that's basically necessary to succeed in industry. I've never seen anything like this where you leave something working and you come back an hour later and it's not working anymore. That's usually not how a file works or like a research paper. You come back and it's still there. This one, that's not the case. Last but not least, it has to be timely. So again, this has to do with how complicated the project is. If it's too complicated, it's going to take us forever to complete it. And we have to make sure that we can complete it in 1 year and not go over that, so that at the end of the year, the students feel like they've accomplished something. We definitely have. I like that. But yeah, you have to make sure that it's not too intense and it's not going overboard. And now I'm going to pass it off to Marek to talk about that.
So I will be talking about our approach, which is active learning through productive struggle. And I believe it is this that makes this class really different from any other class that is taught at this college. It differs from a traditional learning environment where the professor lectures and the students listen and maybe take some notes. What we do is at the beginning of the semester, we get together as a group of students in the class, and along with some input from the mentors to make sure the project meets those SMART goals, we decide what we want to do ourselves. And we have to make sure what we decide is something we can accomplish and that it meets all those goals. What we do then is that we actually research all the components of this project, and then we decide how we're going to make them and how we're going to build them. And it is only when we actually get stuck or find a problem we cannot solve ourselves that we enlist the help of our mentors. So what this means is that we are solving those problems ourselves, and when we don't know how to solve that problem, we already know what the problem is. We found that problem on our own. Then the mentors come in, tell us how to solve this problem. And with that, I believe it's a much more powerful learning approach. And I believe this form of learning is much more powerful than the traditional approach because it really helps us solve real-world problems. And like I said, we discover them ourselves. And because of that, it helps us keep interested in our learning, and it also makes it much more exciting. Next, I'm going to hand it back to Ernest, who will discuss our accomplishments.
Thank you. So our accomplishments, basically, what we wanted to accomplish at the beginning of the semester was, for this one, it was an arm, a robotic arm with 5 degrees of freedom, and we wanted it to be precise enough to where it can pick up an egg off a table and not crush it and break it. For the 3D printer, we wanted to build a 3D printer. If you've never seen one, you've seen one now. This is a 3D printer. And we basically wanted it to be bigger than most of the 3D printers that are commercially available today. There are some big ones in the industry that are worth upwards of $100,000, very expensive. This one is much cheaper and it prints almost the same size as that. So it's a huge accomplishment. What we accomplished so far is we have an arm that has 4 degrees of freedom. As far as the precision and that stuff goes, we'll get to technical details later. And the claws twitching. But yeah, as far as the 3D printer goes though, this is probably my favorite project because I think I worked the hardest on this. We pretty much hit the spot on what we wanted to build. So whatever we had in mind at the beginning of the semester, we got it, and it's working now. So we can actually use it to print whatever we want to design in SolidWorks or AutoCAD or whatever. And with that, I'm going to pass it on to Marek again.
So this is just an overview of how the capstone class is organized. We have the overall capstone class, and we can work on multiple projects simultaneously. So we did the robotic arm and we did the printer. And the class is the people in the class are divided into 3 sub-teams. We have mechanical, we have electrical, and we have software. And those teams, they work together and independently.
Did you use that printer for any parts?
No. That was industrial printer. So this is just an overview of how it's structured. We were separated into groups, and we're all working on 2 projects. So several people work on 2 projects at the same time, so we have to juggle back and forth using that as well. Next, I will give this floor to Kevin.
Thank you. So basically, a set of processes was needed in order to finish this given projects for any of us, and these part of processes included self-learning, communication, and engaging GCC. So, first of all, our approach to the project was self-motivate, to work in a group environment to stimulate the real-world experience, like a workforce, to meet our goals and deliver a functional product, such as 3D printer and arm. In order to do so, researching was required. We researched basically into small bits to modular and take different angle at a time. And after researching it, we'll have to experiment if the idea is possible or if it's not. And that's when basically the documentation comes in. We need to document our ideas, what we did wrong, what we did right, in order to revise in the future and formulate another plan, research even further to move on with the project to actually finish. So, next is the communication. The communication was, of course, very important throughout the project. First of all, I'll be talking about the levels from public level to inter-college level, inter-team, and intra-team. In order to communicate to our other schools, we went to the neighboring colleges such as CSUN, and we also went to other high schools. Other high school has come to GCC in order to see our projects and know what we are building here. And next, we of course want to introduce the program to the college fellow students in order to learn deeper understanding of knowledge and pursue careers in engineering. In order to do so, we of course do these kind of talks, we present, we went around classes, different classes to promote our Robotics Academy. And next level is the inter-team. The inter-team communication was very important because the three teams that Mark talked about had to communicate in order to define what the project was, what the project's limitation, what we're gonna add, and is it possible to add. If it's not, then we need to fix it because mechanical wants to add something, but software can't program it because it's way too complex, then there's a problem. So this is when the inter-team communication comes in and we discuss, we plan, therefore we try to finish our project with given little bits of information from each team. And next, of course, is the intra-team. The intra-team is basically, each sub-team has their own members. The software team had limited members, so it was easy, but other teams had many more members. And it was very important to talk to each other, work together, and actually deliver the goal to the set date. If one person got lazy and did not finish their part, the project would not move on because everyone depended on each other to get their part done in order to move on, move forward, and start building more and more to finish the project, actually. So that was basically the communication part. And next is engaging GCC. Before going on more, first and foremost, we'd like to show our gratitude towards the Technology and Aviation Division, Physical Sciences Division, and the Purchasing Office, and GCC U.S. Department of Education Grants team. Without them, nothing would have worked. We will not have the funding, the proper equipment to do our projects, and we would like to show our gratitude for them. And we would like to cooperate with the GCC in order to promote our Robotics Academy even further on, and share this experience with other students, inspire the students to pursue an engineering careers. And next is the values that we have learned while doing this project. As the project progressed, we have achieved many precious skill sets and set of values. These values include, well, first sets include plans and executing, commitment, and time management. Before starting any project, planning was required. It's a must. It's very important. Through careful planning, we would be able to do a more smooth transition through going through the project and finishing it. But it was clear once we actually started executing this plan, unforeseen conflict just would appear and obstruct us from carrying on with the project further on. So that's when basically the time issues came in. That was one of the biggest conflict that we had. As a student attending GCC, most of us took about average of 16 units per semester, and also on top of that, most of us had part-time jobs. And basically with that, we had to work outside of those classes, not to affect our class. We had to still keep up with other classes, keeping our grade point average, and also finish this product. So we have to learn our time management skills, very important. We have to come in the weekends, late nights, whenever you had time, we would have to manage our time, use it as efficiently as possible. So therefore, commitment, of course, was required because, like I said, we have to come in weekends. We came in Saturday, Sunday, late nights, stayed until 1 o'clock, 12, a lot of times to finish our project. Even yesterday, we stayed until 1 o'clock finishing this little bits of small stuff. So, yes, procrastination, but it happens. So, commitment was very important. Also, summer and winter session. Just because we're not in class doesn't mean that we stop the project, or else we'll not finish any projects. So we actually pushed ourselves to work during winter, work during summer, to actually finish our goals and finish what we planned. And next, Ernest will talk about the next set of values that we learned.
Okay, so the next set of values that we learned is leadership, teamwork and communication, and organizational skill set. The important thing about the leadership is we basically had no leader system in the capstone team, so there wasn't like a top dog that you talked to and he told you what to do and kind of tickled down from there. There was nothing like that. Everybody was the leader of the project, so everybody had to take on their, leader helmet or whatever you want to call it, research their own parts, and make sure that they can deliver and tell the other members about what they learned and what's a good idea, what's a bad idea, what's going to work and what's not going to work. So this is kind of a difficult, it's not difficult, but it's a slippery slope because you have to make sure that people are doing their thing. Because there's no person that Richard can go and yell at, we all get yelled at. So if somebody is slacking off, we yell at them. That's why we're such good friends now. And the other thing is the teamwork and communication thing. This is the really important thing. Like Kevin was saying, if something can't be done on one subsystem, but another subsystem wants to do it anyway, we have to communicate that because something has to change. Either we're not going to do it, or we're going to push the other team to figure something out. Without that kind of a communication, this wouldn't have happened because there's no way that you can build 3 subsystems without anybody talking to one another and they magically work together when they come in. So something has to be done to basically make sure that things are going to work together. And then finally, organizational skill set. We can tell you this personally about the ARM. If you don't document what you're working on, if you're not organized or any of that stuff, you're going to fail. First of all. Second of all, you're going to get cursed at by the next team that takes over. So you have to do it to make sure that you save your name and that you finish the project that you started. It's absolutely imperative. And now I'm going to pass it on to Roman.
All right. Next set of skills that we learned is engineering skills. I first thought this was like opening up SolidWorks, drawing a cup, printing it on a printer, and going like, "Go check this out." That's not what it is. It's actually like learning how to work with other people, how to get something done. For example, these projects. Next thing we learned is technical documentation. That was huge for me. You need to be able to read technical documents. For example, if you want to go up to the machine shop and machine something, you can't just go up there and say, "It's like a circle. Can you like get it done?" No, you need it on a paper, and got screamed at for that. So I know now. Other thing that we learned is presentation skills. I wasn't born in front of an audience, so neither was anyone else. So that's something you pick up, you learn. We've done it so many times. Like Richard and Orman and Dr. Voden, everyone, they've told us like we have to present what we're doing. It's one thing to like sit in the corner and do it, but it's another thing to present in front of other people and also make them understand what you're doing. So I learned that, and we've done like so many presentations that like, I don't know, we're like somewhat professionals at it now, thanks to Richard. I'm gonna pass it on to Marek.
Okay, so finally, the further values that we learned were also problem solving and abstraction. Really, the problem solving, it comes from the way we approach the class. Because we do not get assigned, do this is how you solve it. We get assigned, get to this goal. Find how to get there, solve the problems that go along. We really learn how to approach a problem, how to solve it, how to document that if another person comes to this problem again, they know how to solve it as well. And abstraction is also very important because these are massive projects. They have hundreds of individual components, and while we need to understand all of them, we also need to be able to see the bigger picture, to see how they work together in order to make the completed project work. So abstraction and problem solving are both very big. Next, like Richard mentioned earlier, this is not a club. We do not come here just to have fun. I mean, we are absolutely having fun when we come in, but this is a rigorous program. We need to have some results results. Whether that's a failure or a success, we need to have done something, needs to be documented, needs to be measured. It's absolutely important that we have this done. It is also, apart from the rigor, it is also very technically challenging. It pushes students out of their comfort zones. Personally for me, before this class, I wasn't very comfortable speaking in front of audiences. And like Ernest said, or Roman said, we've done 5-6 presentations now covering what we've done. And it's definitely gotten a lot better than where we started. And so we're doing all these things that we wouldn't normally do. And on the technical side, we also learn skills that we never would have been taught in a regular class. We have to have every single individual component. We need to know how to do it. And that means we get pushed out of our comfort zones and we learn advanced subjects we would not have actually learned otherwise. And next, we're going to actually talk about the projects that we did. Okay, well, the first one is the Prometheus Robotic Arm. It has 4 degrees of freedom. It is mostly 3D printed, and us 4 were the primary people who finished it, but we also received it from a previous group of students, so there was already work done and they had documentation, so we took over their work, we read their documentation, and took the project to a more finished state. Next, I will give it over to Roman, who will talk about the mechanics of the arm.
All right, so the robotic arm, which you see there, this is a CAD drawing of it when we designed it. So it's about the size of a human arm. So what Kevin is pointing at, so if this is, for example, your shoulder, that would be like a human arm. It's about the same size, almost, give or take a little bit. It has 4 degrees of freedom. We were planning to do 5, but it didn't work. But it's largely 3D printed. Almost everything there was done custom. There was no instruction manual. It was just whatever our idea was, we kind of did it that way. It was built, almost everything was built here on campus, so it was printed on our printer, it was machined at our machine shop, and everything was like custom designed. It uses DC motors for joint motion, which Ernest will also go into detail, and we machined some of the parts because we were having problems. So when we first got it, it was like cracked, it was breaking, it was like, it wouldn't work, so some of the parts that had heavier loads on it, which you learn in physics, with a P by the way, not F, you'll learn. We did some of the stuff out of metal, and this is, when it works, that is a CAD rendering, so I actually just figured that out like 3 days ago, so it looks pretty good. It looks just like the arm, and that's what it's supposed to do. And that's kind of like the arm, that's the CAD rendering. So basically everything about the project that we did, we put it in SolidWorks, we put it in CAD, we actually made sure it fit before we made it. It wasn't just making like one part. So we actually did some real world engineering. So if you're in industry, you're going to do exactly the same thing. I'm going to pass it over to the electronics.
Thank you. Okay, so the electronics was also taken over from the last group of students that worked on it. We just had to add a couple of things to it to make it work with our claw and stuff. But basically what you're going on is you have a tiny little microcontroller that's communicating with the software, and it basically tells the motors when to move and how much to move. And then the green boards that are back there, they basically just amplify the signal. The only important thing that you can't see on there right now is actually the encoders. So basically at every single joint that you see there, there's a tiny little device that rotates when the joint rotates, and that basically generates a tiny little signal that the software can pick up, and then they know exactly where the arm is positioned at the moment. So that way they can go ahead and move things around without breaking the arm, like without it trying to go over itself. So I'm going to pass it on to software to talk about the details of that.
So basically, the software team decided to use 2 microcontrollers, which are Arduino Pro Mini and Raspberry Pi. So one of the microcontrollers, the Arduino Pro Mini, is the one that controls the movements and controls the arm of the part of the project. The code was fully student programmed. It was from scratch, and we maintained our program under a version control. And we used industrial standard version control software in order to keep our work safe and also to open to public so they will be able to see. The control of the Prometheus, the arm, contains all joint movements. It includes all 4 degrees of movement with a claw. The Arduino Pro Mini communicates using serial USB to Raspberry Pi to remotely control the arm. And this data includes the current joint angles and any data that was sent from the remote control interface, which Marek will show you in the demo slides later. And without further ado, I'll pass it on to Mark to talk about Raspberry Pi.
So, as Kevin said, there are actually two microcontrollers, Arduino Pro Mini and a Raspberry Pi. The Raspberry Pi is about the size of a credit card, and it's actually a full computer. It has, it's the size of a credit card. It has the processing power of maybe an older laptop. And the Arduino communicates with the Arduino, and together they allow remote control of the arm. What this means is that a user who wants to move the arm can connect to the arm over Wi-Fi, then load up their phone or tablet or whatever they have, and this is actually the interface that comes up. So what you have is a 3D rendering of the arm and its current position. So as the arm is moving, that 3D rendering updates to show you where it is. And then you have sliders underneath that let you set the angle for every single joint. And you also have buttons that let you open and close the claw. And we'll be showing you a live version of this in a bit. And that's it for the robotic arm. Next, we're going to show you some more details about the 3D printer. And to talk about the mechanics, Roman.
Yep. All right, so this is the 3D printer when we inherited it in August. That's what it looked like. We obviously did some work to it, needed a little bit of tweaking. So this is the CAD model of what the 3D printer looks like. We drew the whole thing up because we learned from the first time around working on the arm, make sure it fits on the computer, then it'll probably fit most of the time also in real life. So basically what this is a FDM 3D printer, which is fused deposition modeling. So it adds material versus like a CNC that takes it away. The next thing is it works off of an XYZ coordinate system, so it has a gantry, which you can actually see. It's actually printing stuff, which you guys can also have at the end if it finishes without blowing itself up. It uses linear drive systems, so everything is on like linear bearings, linear rods. It uses stepper motors for motion, which is a different way than we went on the robotic arm, much more precise. It's machine and it has machine and 3D printed parts, so a combination of both. We actually use a 3D printer to build the 3D printer, which is kind of weird, but it works. Everything is custom designed. There was no, again, instruction manual. This was just purely our idea. Actually, if it was our idea, it was going to be a lot bigger and not work, but thank you, Richard. The print size is about 13 by 14 by 8 inches. It's a usable print area, which is actually really big. Most of the printers, like it's about the same size as the Fortis that we have, and that's a little over 100,000. So yeah, it's quite an achievement. And the best part is this one works, and it's actually working now. But look at it now because it might not work at the end. Just in case. We actually learned a lot of engineering skills. This is one thing that I should have learned on the arm. We actually did a lot of FEA, which stands for finite element analysis. So what we did is, since 3D printers have to be really accurate, which I'll explain later, you can't have any like flexing. So if like the whole, if the rods have weight on it and they flex, you need to know that before you design. And we try to do this by hand on the board for 4 hours. Couldn't get the calculations right. And then SolidWorks did it in like 4 minutes. It was great, but disappointing at the same time. So yeah. And that is the 3D rendering of the printer, and that's kind of what it looks like here. So we were pretty close. So, and electronics.
So similar to the robotic arm, we're also using an Arduino for this one, which is just a tiny little microcontroller. It's basically what controls everything else that's happening on there. It's going to be interfacing with the software, so the software team will actually talk about what's going to happen with like a 3D model if you have one, what has to happen so the printer can print it. But the sort of code that the computer generates goes through the Arduino, and then it translates it to motor speeds and directions and stuff like that, and temperatures and all that stuff. And it basically is the big dog. When this thing freezes, everything freezes. Actually, when anything freezes, the whole printer freezes, but that's a technical detail. So to talk about the motor drivers, I'm going to pass it on to Kevin, who is actually on both teams.
So the motor controller. Basically, the motor controller board controls the motors. Sounds like it. The board acts as a link basically between the mechanical and the software. It converts the software commands to electrical signals to control the motors in step and direction. The motor movements carry to the extruder to the correct position to extrude the plastic so we could get an accurate print out of it. The stepper motor is controlled by 2 digital pins basically, which is step and the direction. Step pin basically controls the number of fraction of the rotation the motor rotates every time, and the direction pin controls the direction of it, so it goes either forward or backward. Additionally, we created so that one motor controller is capable of controlling multiple motors because of mechanical limitations. In the beginning, they thought one motor will support this Z-axis. And of course, didn't work out, as some people mentioned, but they didn't listen. But yeah, so we had to make adjustments, and we fixed it, so one motor driver could run multiple motors. And Ernest will finish up by talking about the heaters.
Okay, and then the last piece of the electronics is actually the heater and temperature board. The way that this works is it actually melts the plastic first, and then it deposits it in very precise amounts. So to melt it, we need a heater. Heaters draw a lot of power, so you need a special board that's going to be a big transistor that's going to basically supply that current. And then you have to measure the temperature so that you're not burning the material, you're just melting it. And to do that, we have to have a temperature sensor, which needs filtered power, and it needs to be decoupled from everything else. It's actually the biggest problem that we've been having with this printer so far. But all of those components are put into a separate module themselves. So the reason why we split this up is because it's a huge project, like I said. So we had three groups of people that were working on 3 different parts. And this is what basically the intra-team communication that was happening. We had to come together and basically make sure that everything was going to work in the end. And it did, so we did it right. Kevin?
So for the software, our software team basically consists of 2 components again, which is the PC software and the firmware. I'll be talking about the firmware. It's called Marlin firmware. We forked our Marlin firmware from a different source. Basically, forking means we use already existing code with the modification to meet our needs to run the printer. We decided this method because of the complexity of this given project. If you had to code this 3D printer from scratch like how we did for Robot Arm, we would have never finished. It takes way too long, and it's very difficult. It's not, I say, in our level to program this yet. So we forked it, we used the existing code, but this didn't mean that we didn't have to do anything. We still had much to do. We had tons of things to do. We had to modify all the codes in order to fit our electrical design and the mechanical design in order to fit their needs to move to the correct place with the calibrated and have least errors possible, which I think came down to 0.002 of an inch error, but we're trying to make it better, hopefully. And next, Marek will talk about the PC software of our 3D printer.
So the PC software for a 3D printer actually communicates with the firmware over USB, and the PC software tells the firmware what to do. So the PC software that we use is called Repetier Host. It is standard 3D printer control software, and the reason we can use standard 3D printer control software is because we forked an already existing firmware for the 3D printer, so we didn't actually have to do everything from scratch. So that was very nice. So what the control software does is it lets the user move the printer around the head to make sure everything's working correctly. It also lets the printer select the actual 3D part to print. It then takes that part and translates it into motor commands, which it then sends one at a time to the printer, and the printer makes those movements and actually generates that part. I'll keep it short, but I want to show you guys some demos. So to start with, we have a demo of the remote control interface. So this is an actual live interface for the arm. You have the 3D rendering, which is showing how the arm should actually be positioned. And Kevin. Okay, so now we're actually live. So if I make a change here, if I change the base actually ends up moving. And the nice thing about this interface is that it functions the same way it functions on a computer, it functions on a tablet or on a phone. So you don't have to be in front of a laptop. And I can move the elbow. I can move the wrist. I can do several motions at the same time. So that's just a quick demo of what we can do with the robotic arm. Next, I will hand it over to Roman, who's going to talk about, the 3D printer.
Okay, so kind of to give you a short overview of how a 3D printer works. So if you want to print a solid object, you kind of have to picture this. 3D printer prints in layers like a regular printer does. The only difference is it has a Z stage, so basically it moves up. So if you're trying to print something like this, basically what the computer does is it'll slice it in horizontal layers like thousands of times. So each layer is about 1/3 of a millimeter. So to get a full millimeter, you need to pass by it 3 times. After it does that, what it'll actually do is slice it in the X and Y direction as well. It'll give it tool paths. So the tool paths are basically coordinates that it tells the printer, like, go here, deposit material, as you can see that it's doing now. So after that's done, it takes a while. It melts the plastic, it puts one layer on top of another. It's hot enough to be liquid, but solidifies instantly, and you're left with a 3D printed model. We're actually printing some stuff right now. It should be done pretty soon, but you guys can come up and take them. There's a bunch of them. If you guys have never seen something 3D printed, you can actually have something now that is 3D printed. And that's basically how it works. So this is the interface, and these lines that you see, these are the tool paths. So it passes by each one of those, and it's printing actually on the far one. So if you can see where it's red, that's actually where the temperature, where the plastic is the hottest. So it's going to follow that tool path until it's done. And this is the interface. And that's kind of like a brief introduction into like 3D printing. But you guys are more than welcome to come up and take a look at it closely. Next, I think it's Q&A, right? And I believe next we have the Q&A. So if you guys have any questions, feel free to ask us. We'll be here for quite a while. And then if you want to switch it, let's show the thank you. Go one more. And this is a quick thank you of everything. So questions? Yes. Good.
Specifically, when you're talking about the 4 degree of freedom for
Yes.
the robotic arm, what does it mean?
It means like joints. So how many joints you have? So you have the shoulder. Mark will actually point them out.
So that's actually where the arm can rotate, right? So we have one here that does twisting motion, one here which does this sort of motion, another one which just simulates the elbow, and the fourth one down here which just rotates this way.
So 4 degree of freedom?
Yeah, a degree of freedom is basically just a joint on the arm.
Got it.
You had a question?
I had two, but I'll just ask the first one. Like,
Yeah, nice, Bill.
Like right now, like, have you guys already come up with future plans for revisions on the current projects you have? And if you do, would you pass it on to the next team, or is that something you guys are taking care of?
Perfect. Okay, so his question was if we have revisions and if we're going to pass it on to the next team. So it's never done. If you allow us to like keep. Basically, if they didn't give us a time, like if they gave us a time frame and they allowed us to do like all the ideas we had, it would never get done. So yeah, there's a point where we have to call it quits. This is good enough. There's always revisions, and we're going to pass it on to the next team. So none of these are done. That's not done. This isn't done. It can always be made better. So next year's team, of course, they're going to be working on this, working on that, along with other projects. So yeah, we are going to be passing it along, and we're going to document pretty well so they'll know what's going on.
Yeah, I just wanted to say, part of that handing over the project to the next group of people means we have to make sure we have documentation of what we did, why we did it, and exactly how we did it, so that the next team can read that documentation and continue working on that project. So that's a big part of the class.